Okay, so today we're going to talk about making lines, and what I'd like to start out with is talking a little bit more about slopes. We spent a lot of time on Wednesday describing slopes, and even in the homework thing here we calculated a slope. And a slope really is probably one of the most essential parts of a line in terms of describing its characteristics. Now here I have two lines and they're parallel. Okay, so what I'm going to notice is that if I look at the slope of the top line, it's going to go up 3 for every 4 it goes over, so the rise over run is 3 over 4. The equation to this line is going to be y equals 3x, or 3 over 4x plus 1. The lower line has the same slope. It has a run of 4 and it goes up 3, so the rise over run is 3/4. This one has a different intercept. Notice the intercept of the top line is positive 1, and the intercept of the lower line here is going to be, there's 1 and, oops, too low, and negative 1. Okay, so the intercepts are different, but the slopes are the same. So I'm going to say M1 and M2 are the same thing. So that's going to be the characteristic of a parallel line, is that parallel lines never intersect. And so if two lines were to intersect, you would expect that the values would be the same. At the same x, you'd get the same y if it intersected. But if we look at these two parallel lines and said, okay, here's the first one, y1 equals 3/4 x1 plus 1. The second line is going to be y2 equals 3/4 x2 minus 1. If I set those two equal, that means that they'll have the same y value. If I try and set x equals y, there's not going to be a solution to this thing. So this is the very definition of being parallel to us, is that parallel lines never intersect. So if we wanted to make a line, any line, we can reliably make a parallel line by using the same slope and then some other intercept. If we use the same intercept, we have the same line, but with the same slope. So if I were just to declare y equals 3/4 x plus 10, I'd have a parallel line. Okay, so slopes are the same with parallel lines. Now let's look at something different. Okay, so let's say I have this rectangle. It's going to be 3 high by 6 wide. I'm going to take the diagonal. It's a rectangle, so I'm going to have a right angle. I'm going to take it, I'm going to cut it in half, and I'm going to move that upper half and swing it up like on its side. Now, when I do that, that angle that used to be 90 degrees is now 180 degrees, okay, between the side with the 6 and the side with the 3. So what I've added then is I've added 90 degrees into that thing. And so I have two lines that are perpendicular, those two diagonal lines. So let me consider the slope. Let's look at this first slope of that diagonal line. It's going to be the rise over the run, right? And this one is declining, so it's going to go down 3 for every 6 that it goes to the right. And so we have a -3 and a 6, and so my slope is going to be -1/2 if I were to plot that diagonal line. Now if I'm going to take the other diagonal line and calculate its slope, I'm going to go up 6 and over 3. So my rise is 6, my run is 3. Simplifying that, I get 2 over 1. Now of course I get 2, and I would represent this in an equation just with 2, but just to make a point here, I'm going to keep that as 2 over 1. Notice the relationship between that -1/2 and the 2 over 1. What this means is that if we have two perpendicular lines, the slope of one line is the negative reciprocal of the other. So in this case, I have a slope of -1/2. If I take the reciprocal of that, I get 2 over 1, and I make it positive. So I got the slope there. So if I were just to choose a line, like that line that we had on the previous slide, which was 3/4 x plus 1, a line perpendicular to that would be minus 4/3 x plus whatever intercept that you want. All right, so two characteristics important to remember. One, that parallel lines have the same slope, perpendicular lines have the negative reciprocal of the of each other's slope. Now, one of the ways that we can look at slope, and this example on the board is probably a good example, but we can look at the slope as a rate of change as well. Okay, so let's think of this difference of y over the differences of x as being a over b. So think about this, that for every increase in b units, there's an increase of a units. That's kind of rephrasing this rise over run thing. So for every run of b, you rise a. Okay, another way to say that is for every increase in b units, you're going to increase in a units. And of course, if one of those is negative, then it turns into a decrease, right? But, you know, assuming we're ignoring the sign of a and b, or we're assuming it's positive, then it's going to be increases. If it's negative, then of course it's going to be the decrease. So let's look how we can apply this. So at 1 p.m., let's say I'm riding my bike, and I'm 12 miles from home. I'm riding for 3 hours, and so I'm going to note that I'm at 36 miles from home at 4 p.m. All right, so what I can do here, think about the rate of change. When you're talking about the rate of change of a distance and time, you're talking about a speed, right? That's how fast are you changing position? Well, that's your speed. And so I can calculate that as a slope, where I'm going to take my 2 points, x equals 1, y equals 12, x equals 4, y equals 36. And so if I calculate the slope there, I can say 36 minus 12 divided by 4 minus 1 is 24 over 3, which is 8. So I'm traveling at 8 miles per hour. So that's the essential thing about a slope, is that it tells you the rate of change of something. And just like with this one that we talked about with depreciation, the rate of change of the value of this van was going to be the slope, which we figured was negative $5,000. And so the unit of this is negative $5,000 per year. And so slopes are always rates when you're modeling things. All right, now one of the most important things that I want you to get out of today is how do you make the equation of a line out of a couple points, all right? So the way we're going to do that is we're going to derive this thing from the fact that the slope is constant for a line. Okay, so a straight line has a constant rate of change. And so the way we've defined that is the change in y over the change in x. So for any 2 points that we choose on that line, we get the same m. Now I'm going to make a subtle change to this, and I'm going to say y minus y1 over x minus x1 equals m. And so now I'm saying for any xy, I'm not saying it's a particular point, but any coordinate point xy that's on that line will give me that slope. So if I do a little bit of algebra, and I multiply both sides by x minus 1, all of a sudden here I have the equation of a line, right? I know the point y1 or x1, y1, and I know the slope because I have x1, y1, and x2, y2. I can actually make the equation of the line simply by leaving the x and y in place here. And so if I do an example, and the next slide I'll show you a little bit more general formulas for this. So I want to find the line, the equation of the line through these 2 points, 1, 2, and 2, 5. All right, so first thing I'm going to do is I'm going to calculate my slope. So I have a slope of 3, right? If I take the difference of the y's, which is 5 minus 2, divided by the difference in the x's, which is 2 minus 1, I get 3 over 1, so I get a slope of 3. Now what I'm going to do is I'm going to use this particular form here, and I'm going to plug in a value for y1 and x1. So I'm going to choose this first point here, 1 comma 2, and I'm going to stick it into that formula, and so I get y minus 2 equals 3 times x minus 1. So I'll do a little algebra to solve this, and so I distribute the 3, and then I add 2 to both sides, and I get this equation, y equals 3x minus 1. So that's a derivation plus an example. Let's look at just, the practical way that you're going to do this now. So we're going to call this the point-slope form of the line, where we have a point and the slope, and we're going to apply it to get the equation of a line. So the name comes from this here, that we have the slope, and we have a point that's embedded in here, the x1, y1, and we'll just use that as our format for developing a line. You need to memorize this. Okay, if you want, you can go back to the last slide and remember how to derive it. If you don't like to memorize things, if you prefer to derive it, or just memorize this. The important characteristic here, where people will often make a mistake, is that they fail to put the parentheses around the x minus x1. Okay, so when you're solving this thing, it's important to distribute that m to the x1. All right, so I say you try, but I'm going to do this one. Okay, so find the equation of the line containing 6, 6, and negative 3 and 0. So how would you do that? So the first thing we do is we calculate the slope. So you take the differences in the y's, and so that would be 0 minus 6, and divide it by the difference in the x's, which is negative 3 minus 6. Notice I'm using the parentheses here so I can keep track of that middle negative and not get confused by the negatives that I get in my numbers. Okay, so I have this, then the first step, then I can simplify that by saying negative 6 over negative 9. That, of course, reduces to 2/3. Then I'm going to put it in that point-slope form. Y minus 6 equals 2/3 x minus 6. So I've used this first point, 6, 6, to stick in for my x1 and y1. And now I'm going to first expand my parentheses and then add 6 to both sides. So 2/3 of negative 6 is negative 4, and then I add 6 to both sides, and I get y equals 2/3. Oops, that should be x, not just 2/3. Let me make a correction here. Okay, 2/3 x plus 2. Now, it's unimportant which point you choose. You have to use both points to calculate a slope, right? It takes 2 points. There's no way around that. But you can use either point, and just to make that point, I'm going to actually use the second point. And notice this is a little simpler, okay? So I'm going to put my y1, in this case, which is now 0, and my x1, which is now negative 3, if I'm using this point. And since I end up with just y and I don't have to do anything here, you can kind of choose which point makes the calculation easier. You get to the same thing. So I have x minus a negative 3, which turns out to be x plus 3. 2/3 times 3 is just 2. So I get the same equation. So you can use either point. It's just one of those things that works out that way. All right. Now here's one I really want you to try. Okay, I want you to find the equation of the line through that point, and I'll, on the board here, write the, in case you need the definition. those are the two equations that you use to establish your equation that you're looking for. Okay, so let's look at the solution. First thing we do is we calculate the slope. And so I take my -1 minus 8, the differences in the y's, and then I take the differences in the x's, which is 1 minus a -2. So it doesn't matter which I use as 0.1 and 0.2, so long as I keep them paired right. So the first value in this case was the first point, the second value in this ratio, this difference ratio, is the -2, 8. Kept my signs straight by using parentheses, and so I get -9/3, which is just -3. And so then when I plug in my into my point slope form, that first point and the slope that I just calculated, I get this equation, and now I'm going to simplify it to first make the y minus a -1 into y plus 1, distribute that -3, so I have -3 times -1 will give you +3. Subtract 1 from both sides and I get y equals -3x plus 2. Okay, is that what you got? All right, good. Now we're going to find some equations of different lines. So let's find the equation of a line parallel to y equals 5x minus 6 and through the point 1, 7. So this, as it turns out, really is easier than the problem that we just did, because what you know about parallel lines is that the slopes are the same, right? And when you have y equals 5x minus 6, what's the slope? 5, right? Okay, so we can just go ahead and put that point into the point slope form, and then we expand the parentheses and we move the -7, add 7 to both sides, and we get y equals 5x plus 2. So fairly straightforward calculation. It all depends on knowing this formula here, or this method, I should say, of establishing the line. Now you don't have to check these, but if you're interested in checking them, the way you do it is you just plug in the x, and so y equals 5 times x equals 1, in this case, plus 2, and so we get y equals 7, and so that's the coordinate pair that we were looking for. And then the other check is that your slope is the same, which is 5 in both cases. Okay, so now we're going to go back to the perpendicular lines and say, I want a line that's perpendicular to the line that's established by 1 and -3 and 7 and 9, and going through the point 2, 3. All right, so this one is a little bit more involved. What we want to do is first find the equation of the line through those 2 points, figure out what kind of slope our perpendicular line has, and then use that in our point slope form to calculate the equation. Okay, so we calculate the slope first of that first line. So we take 9 minus a -3 divided by a 7 minus 1. And so we get a slope of 2. And so we know that the slope of the perpendicular line that we're looking for is the negative reciprocal. So the negative reciprocal of 2 is -1/2. So you make that a ratio, turn it upside down, put a negative sign in front of it, or if it has a negative sign, make it positive. And then we stick that into our point slope form. We want it to go through the point 2, 3, so we stick that in there, and now we expand the parentheses. And then we add 3 to both sides, and so we get our equation y equals -1/2 x plus 4. So it involves two steps. You know, we didn't really ever calculate fully the equation of that line. We're just looking at the slope because that's all we're interested in. We know that the point that we're going to go through will establish that line. So where that original line is really unimportant. It's really what's the slope of it. So let me draw a picture of it. If we make our axes, and I'll start with just a couple points because I don't know the equation of the line. So I have my 2 points. You can see them here, which is the 1, -3, and then the one up a little higher, up there. And so I'm going to take a straight edge and draw a line through it. And there's the line. And then the 2 points to the equation of the line that the perpendicular, this is the point that I want to go through, right? That's 2, 3. And then once I get my equation, this thing down here, notice my intercept is 4. So I know that when x equals 0, the line that I'm talking about will go through the y-axis right there. And so there I have 2 points, and I can make my line, and I get this perpendicular line. And so depending on how carefully I drew this, you know, that should look like perpendicular lines. Okay, so we're going to have 3 different forms of linear equations, and they all have a name. We've talked explicitly about 2 of them. That y equals mx plus b is probably the one that you'll see most linear equations in. That's called the slope-intercept form. Called that way because you can read right off of the equation what the slope is, and you can read the intercept as being b. We just have been dealing with the point-slope form, so we have a point and a slope, and we can make that equation. That first one is called standard form, ax plus by plus c equals 0. And this form conforms to the standard form of many different kinds of equations. And occasionally you'll see an equation like that. Sometimes you'll see the c on the other side of the equality sign. And it turns out that in that form, notice there's no m in there. You have to actually calculate the m. And so the way you do that is that you solve for y and see what the coefficient is for the x. Okay, so remember those 3 names and what the forms are. So what I really want you to take away from with linear equations is that you can do these things. I want you to be able to calculate, given 2 points, I want you to be able to calculate the line, calculate its slope. If I give you a line and a point, determine something that's parallel to or perpendicular to that line. And then, given a graph, determine the equation of the line. And given an equation, make a graph. Let me stop right there for a minute. Now, the way you do this is recognize that 2 points will establish a line. So when you're making a graph of a line, you can do it the way that we did originally, where you start with the intercept and count off the rise and the run to get your line. Or you can just put in 2 points that are spaced apart, plot those 2 points and draw a line between the 2 of them. Okay, that's one way. Then to make an equation from a graph, what you do is you do the opposite. You read 2 convenient points off the graph, and you use those 2 points as the starting point to make your equation. So there's, if you can do the first thing, given 2 points, you should be able to do the last one, which is, read it off of a graph. You can all read a point off of a graph. And so here the key thing is just to take the easy points. If the intercept is very obvious, then that's a good one because zeros are it involves a 0, comma, intercept, and that's always an easier number to deal with than when you're dealing with two numbers. And so when we have these equations to actually read off the slope and the intercept, the way you do that is you put it into that slope-intercept form so you can read the m and the b off directly. So regardless of what form of the line that you get, you should be able to convert it into y equals mx plus b, tell me what the slope and the intercept are. And then also, you need to be able to write the equation of a vertical and horizontal line. Now think about what those things are, and I think we plotted this on Wednesday. A horizontal line has a 0 slope, so it's just y equals some value. The vertical line, the slope is undefined, and so it's just going to be x equals a value. Okay, so let's look at an application of this, and then for the remainder of the period, I'll put up a few things for you to try, and I'll talk about the milestone that we're gonna do that's related to linear equations. Okay, so let's say Bill rented a car. He drove 200 miles, paid $95. Katie rented a car, drove 150 miles, and paid $85. So what the rental company does is it charges you a daily rate plus a per mile rate. And so what we want to do from these two data points is establish what our rate structure is. So our 2 points are, if you drive 200 miles, it costs you $95. So in this case, you know, the x value is 200, the y value is 95. Second one, at 150 miles, you're paying $85. So when you're doing these applications, it's important to establish which one is the first value and which one is the second value. We call the first value the independent value. That's the one that's the input. If you drive 200 miles, the output is it's going to cost you some money. And so, you know, make some decision based on that, what the order should be. And so here we can calculate the slope. And so we look at 1/5. Now I'm going to make a little departure here from my usual ranting about keeping integer ratios. My slope is 1/5. In dollars and cents, we're talking about a rate. We're talking about a dollars per mile rate. And so 1/5 means 20 cents a mile. So when we're talking about money, you know, it's better to use dollars and cents because that's what everybody understands with money. So here's a 20 cent per mile. That means that those extra 50 miles that Bill drove cost him an extra $10, right? So 0.2 times 50 is 10. So that's the rate that you accumulate on your mileage. And so if we put that in our point slope form, we can calculate what the equation of the line is, and from that we'll read directly what the slope and the intercept is. So the daily rate is 55 miles. That means regardless of how much you drive, you're going to pay 55 miles, and then depending on how many miles you drive, you're going to spend more on that. It's going to be at a rate of 20 cents per mile.